Hello my dear students, welcome to my YouTube channel Next Gen Math. So today we are discussing an engineering mathematics concept, that is complex variable. So you are already aware the complex word in class 11, that is in complex number chapter. Okay, so how you have defined in class 11 is that, so z is equals to x plus I y, or sometimes it is defined as a plus ib also, where these x and a are real parts and y and v are imaginary parts. Okay, and similarly if you apply function to it, it becomes f of z, and this is called as complex function. This is complex number and this we represent it as complex function, and this is defined as u plus iv. This is complex function. Okay, and here also u is a real part and v is an imaginary part. Okay, so this is about the definition or the difference between the complex number and the complex function. Okay, and today here we are discussing an important derivation, that is the Cauchy-Riemann equation in Cartesian form. We have two forms here, one is Cartesian form, another one is polar form. So today we'll discuss the case 1, that is CR equations in Cartesian form, and most commonly this is asked in engineering mathematics subject, either in 3rd sem or in 4th semester, wherever you are studying. So this is asked as state and prove CR equations in Cartesian form or polar form. Okay, so today let us see the first case. Okay, first let us write the statement in an easy way. Let us see. Okay, so there is a condition, a necessary condition, f of z is equals to u of x comma y plus I into v of x comma y, and this is analytic about a point z is equals to x plus iy. This is very simple statement. Okay, and there exist 4 partial derivatives, that is ux, uy and vx and vy, such that ux equals to vy and vx equals to uy, and these two equations we call them as Cauchy-Riemann equations in Cartesian form, and these we are going to derive here. Okay, and you can observe this f of z is given a function, and he said it is analytic at about a point. So by the definition of analytic point, using this given function we need to derive initially. Okay, let us see. By the definition of analytic function here, okay, what we have, f dash of z is equals to limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z. Okay, this is a definition, and he has given already f of z here. You can see f of z is already there. What we need f of z plus delta z. Okay, this function is as same as f of z, but he has added delta z, so we call it as a small increment in z. Okay, it is been added, so you can say delta represent a small change, so he has added, so we say it is a small increment in z. Similarly, you can change x as x plus delta x and y as y plus delta y. We say that delta x and delta y are increments for x and y. Okay, let us see. Let us write that equation here. F of z plus delta z. F of z is already given, and I'll write z plus delta z. So what you do, just replace x as x plus delta x. Here it is, comma as it is, and y as y plus delta y. Same for the imaginary part also. Okay, let us see. So again x plus delta x comma y plus delta y. Now let us substitute these two functions into the definition. What it becomes? F dash of z is equals to, as limit delta z tends to 0 as it is. I'll use this as this whole part. Let us see. Okay. Here u is missing. Let us take u. So u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y. This is the whole first part. F of z plus delta z. Okay. Now minus of f of z. F of z is already given in the statement. Use here. What it becomes? U of x comma y plus I into v of x comma y. The whole divided by the formula delta z remains as it is. The formula delta z remains as it is. Now what you do, the next step is very important. Just separate the real parts and imaginary parts. Okay. This is your real part, and here also one you have real part. Just separate them. And what I do is, I'll take the separate limit and separate denominator to the real part as well as imaginary part, because that equation will be the key equation for further simplification. So okay, let us see how it becomes. Limit delta z tends to 0 as it is. The first real part is this one. I'll keep it here. That is u of x plus delta x comma y plus delta y. The next real part is here, minus of uxy. Minus of uxy divided by this delta z as it is here. Okay. Now next part plus this is your imaginary parts, the red mark. Okay, in both of the terms I is common. You can see here. I'll take I as common here. Separate limit delta z tends to 0, and this is v and that is v. Okay, that is it. V of x plus delta x comma y plus delta y, and here it is minus into plus is minus v of x comma y divided by this common delta z to both the terms as it is. Okay, and we call this as the main equation. By this only we are going to derive the further derivation. Okay, is it clear now? You can take out the screenshot for your notes, or you pause it and write down the okay. Okay, we'll continue further. So I'll rub this. Next, let us consider an equation delta z. Okay, now what you do, I'll add by z and I'll subtract by z to it by considering delta z. So I'll make this as one term and z as another term. And already you know, we know that z is equals to x plus iy already. Okay, and delta z plus delta z becomes, just increment it, x as x plus delta x plus I as it is, y as y plus delta y. Simple. Use these two here and simplify. What you will get? This implies delta z is equals to this concept as x plus delta x plus I into y plus delta y. Okay. This minus as it is, and z value is what we have? X plus I. And now simplify, open the braces. What you get? You can cancel x with x because plus x minus x, and I into y with I into y. The remaining terms will be what? Delta z is equals to delta x plus I delta y. This is equation 2. Is it clear till now? Okay. How to create, make or derive till equation number 1, and considering delta z and adding subtracting by z on both sides and using these two values here, and on simplification we'll get this equation. Okay, let us see. Now we have two cases here. Case 1, what you will do is let delta y is equals to 0 in the case 1. Where to substitute? In equation 2. Let us see what this equation becomes. Equation 2 becomes delta z is equals to delta x, because delta y is 0. This is one term we obtain, and also as initially we have delta z tends to 0, you can see here delta z tends to 0. What we obtain delta z as delta x, delta z as delta x, and this implies our new limit will be delta x tends to 0, and using these in equation number 1. Equation number 1 implies f dash of z is equals to limit delta z changes to delta x. Let us substitute here delta x tends 0, and you use delta y as 0, and wherever delta z is as delta x. Let us see. Here it is equation number 1. U of x plus delta x comma y, because delta y is 0, minus u of x comma y divided by delta z as delta x plus I as it is. Again limit will be delta x tends to 0 here also. Substitute delta x as, delta y as 0. V as x plus delta x comma y minus v of x comma y divided by here also delta x, because instead of delta z we have delta x. Okay. Now this equation is like the basic definition of the partial derivatives, u with respect to x and v with respect to x. Okay, with the help of the basic definition of the partial derivatives. By the definition of partial derivatives, we have f dash of z is equals to 2u by dou x plus this I as it is, this as dou v by dou x. I'll take this as equation number 3. This is the case 1. Again we have a case 2. We have chosen delta y as 0 here. Next we need to choose delta x as 0 for the case 2. Again substituting in equation 2, and the result will be used in equation number 1 only. Okay, equation number 1 only. So you remember this equation first. Okay, I'm going to rub this because we need to write down the next things. So we'll find the second case and substitute all the data into equation number 1 as of case 1. Let us see. What is case 2? Let delta x equals to 0. Where to substitute in equation 2? Let us see. Equation 2 implies, so delta z will be I delta y. If you substitute delta x as 0, it will be I into delta y. But as delta z tends to 0, this implies while writing limit, we don't consider the imaginary part. Keep in mind. So what we did? Delta z as delta y. Okay. Again substituting all in equation number 1 only as of the previous case. Let us see how it becomes. Equation number 1 implies f dash of z is equals to limit. The previously it was delta x. It will be delta y. Delta y tends to 0. Now use it as x, delta x as 0. How it becomes? U of x comma y plus delta y, because delta x is 0, minus u of x comma y divided by, here it will be I delta y. Why? Because delta z is I delta y, plus this imaginary term as it is, limit, it becomes delta y tends to 0. Now v of x only as of the u term, because delta x is 0, y plus delta y as it is, minus v of x comma y, divided by, here also delta z as I delta y. But what I can do here, I can be cancelled, okay, and we'll simplify this further. Okay, you just take the screenshot of this, or else you can note it down by pausing. We'll continue it. Okay, take the screenshot. Okay, did you take it? Okay, let's see. Okay, move forward now. What it becomes? F dash of z is equals to, now here also we know that 1 by I can be written as minus I. By rationalizing the denominator, you can write 1 by I as minus I, because I should not be kept in the denominator. As you know, the concept of the complex numbers, I should not be kept in the denominator. If it is in the denominator, what we do, we rationalize the denominator by taking the conjugate, multiplying, dividing. Okay, so otherwise you just directly remember it as 1 by I is minus I directly. I'll use here the first term. Okay, what it becomes, f dash of z is equals to, this is minus I u of x comma y plus delta y minus u of x comma y divided by delta y, plus here I have left the limit also, limit delta y tends to 0, again limit delta y tends to 0, v of x comma y plus delta y minus v of x comma y divided by delta y. So this is also by the definition of partial derivatives. Again, what we have is f dash of z is equals to minus I as it is. This will be dou u by dou y plus dou v by dou y. This is equation. I think we're almost at the end of this derivation now. Okay, what you do is, what we'll do is, we have equation 3 and 4 here. We'll equate equation 3 and 4, because you can see LHS are same. We can equate their RHS, f dash of z and f dash of z. Here also equation 3 and 4. Okay, equating equation 3 and 4. 3 and 4. Okay. What we'll get? Equation 3 is dou u by dou x equals to plus I into dou v by dou x. So minus I dou u by dou x, dou y is plus dou v by dou y. Now only one thing is, we are at the end of the derivation here. What we do is just equate the real terms and imaginary terms. Equating coefficients of real and imaginary parts. Real parts are dou u by dou x equals to, here it is, dou v by dou y, and imaginary parts are dou v by dou x equals to minus dou u by dou y, or in short form it is written as ux equals to vy and Vx equals to minus Uy. So these are okay. Whenever we are equating, you need to leave the I terms because we are equating the coefficients, not imaginary term. Okay. So this is these two are the real terms and these two are the imaginary terms, and this is what we have written at the during the statements at the beginning of the derivation. So we need to derive the terms of the Cauchy-Riemann equation. So that is Ux equals to Vy, Vx equals to Uy minus Uy. So this is called as the Cauchy-Riemann equations in the form of Cartesian, and this is the derivation. So this is the easiest way to learn the things. Okay, again, if you have any confusions, again go through with the video from the beginning and write down it once and just move forward. Okay.